How's it going, ladies and gentlemen? Mr. Donnie here once again. This time we're going to take a look at ionization energy. So our objectives are to describe the patterns that emerge as a result of the organization of the periodic table and the underlying reasons for these patterns. Describe the exceptions to the trends and the underlying reasons for them as well, and use these patterns to predict the properties of related elements. All right, so ionization energy, let's talk about what it is. It's the minimum energy required to remove an electron from the ground state of the isolated gaseous atom or ion. Basically, it's just how much energy does it take to rip away an electron. So it's always going to be a positive value because these electrons are negatively charged and the nucleus is positively charged. So they're attracted to each other. So if we're trying to rip it away, it's always going to require putting in some energy. All right, so notations. When they talk about ionization energies, they could be talking about the first ionization, the second, the third, or the fourth. And all that's really saying is, all right, if you see an I with an underscore 1, you're talking about the first ionization energy, and it's the amount of energy required to remove the first electron that you're ripping away. So after that, we just change the 1 to a 2. If you're ripping away a second electron, little subscript 2, there you go on, so on and so forth. All those little subscripts are telling you which number of electron you're ripping away. So 1 is the first, 2 second, so on, so forth, and what have you. All right, so successive ionization energy is talking about, all right, how do the ionization energies change as we start taking 1, start taking 2, 3, or fourth one, and so on, and what have you. So the first ionization energy is always the lowest. It's always easiest to rip away the first electron. So if you see I1 right here, it's got 578 kilojoules per mole. And if I take a look, all right, well, once I've ripped one away, so if I have aluminum, its configuration is 2-8-3. So once I rip one away, now my configuration is 2-8-2, and I have an aluminum with a positive charge because I just removed one electron. So now it's going to be harder to remove another electron because they're negatively charged. So, all right, well, it's one thing ripping away an electron from a neutral atom. Now I have this positive ion that I'm going to have to rip away a second electron and then make Al plus 2. So you can see how does the second ionization energy compare to the first one. It's a lot greater because, hey, you're pulling an electron away from something that's already positively charged. It really wants to be there. And you can see, again, Al plus 3. The third ionization energy is a lot greater than the second one even. And then we take a look at I4, and this is background in a different color because this is a lot greater, and we'll get into why like right now. So if I had aluminum, which I do right here, all right, it has 3 valence electrons. If I want to rip one of those away, I'm going to have to invest that many kilojoules of energy. If I want to rip a second one away, I'm going to have to invest this much more energy. If I want to rip a third one away, I'm going to have to invest this much energy. Now what happens? Once I've eliminated those 3 electrons, well, aluminum was 2-8-3, and now I've just ripped away those 3 electrons, and I'm getting to the core electrons. It's no longer the valence shell. So now, if I wanted to rip one of these electrons away, it's going to be a lot harder. And you can see that in the values for that ionization energy. Once you get to the core, for aluminum, it's the 4th ionization energy. It's a lot harder to pull an electron away. All right, so trends for ionization energy. As you go left to right across a period, the first ionization energy tends to increase. So as you go left to right, it tends to get harder to remove an electron. So you can see right here is the start of period 2, and right here is where the end of period 2 is. So as you go left to right across a period, for the most part, ionization energy increases. Same thing, here's period 3. Overall, it increases going left to right. And you see that trend across the rest of the periods. As you go left to right, the ionization energy tends to increase. Well, why? Why does it do that? And the short answer is the effective nuclear charge. So let's take a couple examples to look at. I got lithium, carbon, and fluorine are going to be the ones that I focus on. Lithium's effective nuclear charge is going to be +1. Right, so if I look, lithium is 2-1, so the effective nuclear charge on that valence electron is going to be the 3 minus the 2 shielding electrons, so it equals +1. I look at the same thing for carbon, it's going to be +4. I look at fluorine, it's going to be +7. So the electrons, if I'm looking at lithium, this is my nucleus, energy levels, and I have 1 electron here. Well, it's going to be easier to pull an electron away that's feeling a +1 charge, as compared to with fluorine, an electron that's feeling a +7 charge. So it's going to be harder to pull away fluorine. That's why generally it increases. I keep saying generally, and we'll get into why it's not always. But first, moral of the story is smaller atoms, they're harder to remove electrons. They're holding those electrons closer, they're holding onto them more tightly. And the reason they're smaller is because of a stronger effective nuclear charge. So they're harder to remove. So what's with those exceptions? So the trend is as you go left to right, it increases. But if you see, there's a couple of places that's not true. So right here, right there, hey, I see that. Again, there's a pattern forming. There's a couple of exceptions. So there's exceptions between beryllium and boron, magnesium and aluminum, as well as between nitrogen and oxygen, and phosphorus and sulfur. So let's get into why they are the exceptions. So between groups 2 and 13, what's happening here? Well, group 2, like lithium right now, that's 1s2, 2s1, but then when I get to beryllium, now it's 1s2, 2s2. Okay, but then why is boron easier to remove a valence electron? Well, let's take a look at its electron configuration. It's 1s2, 2s2, 2p1. So we're starting to add electrons to the p sublevel. So the s sublevel does a better job at shielding other electrons than the p sublevel does at shielding other p electrons. So p is at a higher energy level than the s sublevels. So once we get to boron, hey, yeah, that p electron is going to be easier to remove than this, s electron. So we get a little dip there. You're also going to see that in period 2. Again, between groups 2 and 13, you're going to see that exception to the trend because of transitioning from filling the S sublevel to the P sublevel. So you'll see this exception in the same place where we're transitioning from the S sublevel to the P sublevel in other periods. So you can see it in this first period, the second period, the third period, and you see it throughout. So those are the exceptions, and the reason that you see them, well, it's happening, the same thing's happening in the same place. It's transitioning from filling the S sublevel to the P sublevel, and the P electrons are easier to remove than the S. The other place you see exceptions is between groups 15 and 16. So right here you can see, hey, this didn't follow the trend. It actually went down in ionization energy. Why is that? Well, in this example, we're going to again have to take a look at the electron configuration. So here the P sublevel has each of its 3 orbitals filled with an electron in group 15. So if I'm taking a look at nitrogen and I'm looking at just the P sublevel, it looks like this. It's got 1, 2, 3 electrons in the P sublevel. So that's for nitrogen, right? But when we're going to oxygen, now we have to start pairing them up. I put in 1, 2, 3, and then I have one more electron. It's got to go there. So why is that electron easier to remove? Well, electrons repel each other. So when I pair them up and I start putting a second one in the same orbital, in the same box as another one, they repel. It's going to be a little easier to remove. And again, you're going to see this exception in other periods as well. That's this dip right here, where we're transitioning from having 1 in each p orbital, and we're transitioning to pairing up electrons in the same orbital. So again, same thing's happening in other places, and we start to see how it deviates from the overall trend in some places. All right, going down a group, a little more consistent. As you go down a group, the first ionization energy tends to decrease. The atoms have additional energy levels and get larger, so those outermost electrons are further away from the nucleus and are easier to remove. So the bigger it gets, the easier it is to remove. So if we just take a look at the noble gases, helium, neon, argon, krypton, xenon, you can see there's an overall trend of decreasing as you go down a group. You can also see it in the the group 1 stuff. Although it's not as apparent, you can see it starts to decrease. I can't draw that straight, but yeah, there you go. So going down a group tends to decrease. So let's do a little practice. Pause it. Try to put these in order based on what you know about the trends. We got neon, phosphorus, sodium, argon, and potassium. Press play when you're ready for the answer. All right, well, let's take a look. What elements are we looking at? We're looking at neon. We're looking at phosphorus. We're looking at argon. Oh, I skipped some. We're looking at sodium and potassium. So if I'm taking a look, let's start with the ones that are in the same period. So I know that the ionization energy increases as we go left to right. So I know that sodium is going to be less than phosphorus, which is going to be less than argon. So now if I'm taking a look at argon and neon, well, neon is smaller. And what do they say about the size? Well, the smaller they are, the harder they're holding on to those electrons. The bigger they are, the easier it is to take it away. So we know that neon is holding on to them pretty tight, so you're going to need a greater ionization energy. So now the last one that I got to worry about is potassium. So, well, it's near sodium. Let's think about this. Again, potassium is bigger than sodium, so it's going to be easier to rip away that outermost electron. So potassium is going to have a much smaller ionization energy. There you go. So summarize. Describe the patterns that emerge as a result of the organization of the periodic table and the underlying reasons for these patterns, as well as describe the exceptions to the trends and the underlying reasons for them, as well as use these patterns to predict the properties of related elements. I hope you found that helpful. I'll see you in class. Okay, bye.